Welcome to this explainer. Today, we're diving straight into a totally fascinating space where raw, high-speed data collides with physical reality. We're talking about digital twins on Google Cloud. If you've ever wondered how modern smart factories are literally coming to life, transforming massive streams of abstract data into highly visual, interactive 3D environments, you are absolutely in the right place. Let's get right into it. Picture this. You're standing right in the middle of a massive 100,000 square foot factory floor. Now, traditionally, you'd be staring at a standard IoT dashboard that's just throwing a relentless stream of raw JSON telemetry at you. Suddenly, you get a flashing red temperature alert. Okay, something's wrong, but where is it? You have zero spatial awareness. That alert tells you what is failing, but finding the exact physical location of that asset, that costs crucial, sometimes disastrous minutes. But what if, instead of lines of code, you were looking at a fully animated, interactive 3D CAD model of that exact robotic cell? That is the real challenge, bringing those two worlds together seamlessly. So how do we solve this spatial context problem? Well, it happens by completely bridging the gap between raw numbers and physical geometry, by mapping real-time sensor streams directly onto 3D spatial models, like building information modeling or BIM and CAD geometry. We stop staring at abstract metrics. Instead, we're transforming them into intuitive, actionable 3D visual intelligence. You're no longer just trying to decipher numbers on a screen. You're actually watching your data live, right inside its physical space. To really wrap our heads around this, we have to understand that a digital twin is not just a static visual. It's not just a pretty 3D picture. It is a living, breathing, evolving virtual replica of a real-world system. It doesn't just show you the shape of a machine, it continuously analyzes how that machine functions. We're talking about tracking everything from the real-time rotation of a physical shaft to its exact thermal conductivity, constantly updating itself using a live flow of data, sensor input, and user feedback. It literally learns and adapts to mimic reality with just incredible precision. Building this out practically requires a seriously robust, serverless Google Cloud architecture. And the data journey here is just amazing to trace. It kicks off right on the factory floor, with physical sensors streaming live data directly into Cloud PubSub. From there, Dataflow steps in to enrich that stream with spatial IDs, basically giving the data its exact physical coordinates. Next up, Bigtable handles all that high-frequency time series data. Then Vertex AI takes over to run predictive simulations. Finally, an API layer renders all these dynamic updates straight into high-fidelity 3D gaming engines, like Unity or Unreal, or even a WebGL dashboard. It's a completely unbroken, high-speed chain from a physical sensor straight into a fully rendered 3D environment. If we look inside the engine room of this pipeline, you'll see these specialized tools working in perfect harmony to drive live visual demonstrations. Dataflow acts like your master cartographer, mapping sensor IDs to exact spatial coordinates so the system knows precisely where every piece of telemetry belongs in 3D space. Bigtable, that's your ultra-fast memory bank, supplying the low-latency reads you need to keep a model updating smoothly in real time. And Vertex AI acts as the brain of the operation, analyzing trends to actually simulate future wear and tear. This means operators can run complex what-if scenarios right on the digital replica without ever having to touch the physical machine. So, what does bringing that pipeline to life actually look like? Imagine you're tracking the real-time thermal conductivity of a robotic joint bearing. As the data shows a critical failure threshold approaching, we map it through Google Cloud directly onto the 3D asset. We're literally rendering a live heat map right onto the physical joint of the robotic arm in 3D space, exactly as that physical asset approaches its limits. It gives you this immediate, highly visual warning that is basically impossible to misinterpret. The impact of this kind of active monitoring on live factory operations is staggering. Take industrial robots performing super-sensitive milling tasks, for example. Normally, the massive forces involved in manufacturing can actually push the robot slightly off its intended path, which leads to inaccurate movements and ultimately ruined products. But when you have a digital twin connected to live telemetry, those massive forces are calculated and simulated instantaneously. The twin then triggers the physical robot to compensate in real time, keeping its movements perfectly accurate and right on path. This brilliantly highlights the real-world impact of testing and simulating in a virtual space long before you ever build a physical prototype. By leveraging digital twin technology, Siemens was able to develop a world record-setting electric aircraft motor. And the result is mind-blowing. They created a motor that weighs just 50 kilograms, but is a massive 5 times more powerful than comparable electric motors. That kind of exponential leap in innovation, it's really only possible when you can flawlessly simulate behavior and iterate over and over again in a virtual environment. But wait, it doesn't stop at just simulating existing designs. Digital twins also unleash the full potential of modern manufacturing techniques, like 3D printing. In a recent study looking at gas mixing systems, Siemens combined flow simulation insights with generative AI algorithms. The AI ran through countless twin simulations to find the absolute optimal flow. And what it came up with was a truly unique, organically shaped channel configuration that is wildly more efficient than any traditional shape ever designed by human hands alone. Now, bringing this all back to the factory floor and the actual people running it, this completely changes the paradigm. Remember that flashing, stressful red JSON alert we talked about at the beginning? When a critical overheating alert fires now, the whole dynamic is different. A plant manager walking the floor with an industrial tablet doesn't have to guess or manually search for the problem. They just look at their screen, and the digital twin provides the exact spatial location instantly. They can visually pinpoint the failing bearing right there on the interactive 3D model. And this is where interactive spatial troubleshooting really shines. By fusing that spatial context with live predictive analytics from Vertex AI, operators get an unprecedented level of operational visibility. When they tap on that red overheating bearing on the 3D model, a menu instantly pops up. It streams the predicted time to failure based on real-time data and gives them a one-click option to reroute production or trigger maintenance on the spot. When you can predict the availability of the plant in parallel to your actual operations, sudden, costly disruptions basically become a thing of the past. As incredible as all of this is, we're really just scratching the surface here. The future is all about merging these digital twins directly with artificial intelligence to completely break traditional design paradigms. We're talking about a shift from human-led product design to a reality where AI independently designs advanced custom products. Siemens is actually realizing this potential right now by partnering with a California startup called Hackrod. Together, they're using digital twins and AI to let computers independently design fully customized sports cars. The twin isn't just a reflection of reality anymore, it's actively creating it. So we've seen how transforming raw JSON telemetry through Google Cloud's PubSub and Bigtable into interactive 3D spatial models changes absolutely everything. From rendering real-time heat maps right on factory equipment to triggering those complex Vertex AI simulation pipelines, digital twins are turning factory floors into highly interactive, self-diagnosing, and even self-designing systems. As we wrap up this explainer, I want to leave you with this. When you can finally bridge the gap between abstract numbers and physical reality, what extraordinary possibilities will you unlock? What massive problem are you going to solve when your raw data finally takes physical shape? Thanks so much for exploring this with me today.